What is going on, guys? Welcome back. In today's video, we're going to use machine learning to predict the most likely winner of a CSGO match, of a CSGO round, given a lot of information about the current state of the round. So let us get right into it. Alright, so for this video today, we're going to use the CSGO round winner classification dataset available at OpenML. You will find a link in the description down below so that you can download it for yourself. And this dataset contains a lot of information about the game, about the state of the round, stuff like how much money does the T side have, how much money does the CT side have, is the bomb planted or not, how many players of each team are still alive, what kind of weapons do the two teams have and stuff like that. And then we also have the information about who won the round actually. And we have this information every 20 seconds of each round, or for each round. So basically the round starts and every 20 seconds we have a snapshot. What's the economy like? How many players are alive for each team? Is the bomb planted or not? And other stuff. And in the end, we have then the winner of the round. So for each row, we know who won this round and we have the current state of the round. And based on that, we can train now a machine learning model to get all this information to predict who will win this particular round. This is what we're going to do today. Here you can see the description of the dataset. You can also, as I said, click on a link in the description down below. You get the information that every 20 seconds we get new data, and you can also see what exactly this data is. It's from competitive players, I think, so from pro players and stuff like that. You can read all of this here in the page, and you can download the dataset by clicking on download here. I'm going to use the direct download link so that we can download it in our Jupyter notebook. I'm going to use a Jupyter notebook for this video today, just because I enjoy doing that when doing some data exploration, visualization, machine learning stuff. So I'm going to open up a new Jupyter notebook here, and we're going to start by importing requests. By the way, you're going to need to have the basic data science stack installed. So what is that? You want to run pip install pandas, numpy, matplotlib, probably seaborn as well, scikit-learn for sure. Maybe if you want to go into deep learning here as well, we're going to look at this, probably TensorFlow, and also requests, obviously, because we're going to now download the package. So just install the packages that you're missing. This is not a beginner tutorial, so I'm not going to explain all the details here, but you should have the basic Python data science stack on your system. So we're going to import requests, and then what we're going to do is we're going to say URL equals, and I have here the URL prepared already. You can copy it from me, https://www.openml.org/data/download, and then the number is 22102255/dataset. This is the URL of the CSGO dataset. We're going to just say r equals requests.get. We're going to get that URL, and we're going to allow redirects so that we can actually get it. And when I run this now, I get the response, and I can now write this response into a file. I can say with open dataset.txt, write as bytes, SF. I want to write the content of the response, which is going to be just a file. So I can open it now, hopefully, if it's not too large. And you can see here we have a bunch of comments, we have some attributes here, and then we have the raw data, which we can load into a pandas data frame. So what we're going to do now is we're going to say, first of all, import pandas as PD. And we're going to then say, that we have an empty list called data, and we're going to open our data set that we just saved in reading mode, SF. And then we're going to split on new lines so that we can extract the actual attributes in the comments so that we only have the raw data. So we're going to say here for line in f.read, we're going to split on line breaks. So split on \n. For each line that we have here, we're going to say if the line starts with, this is a string function. If it starts with an at, it's an attribute. And if it starts with %, it's a comment. Or if the line is a blank line, then we also want to exclude it. In all these cases, just continue. So just continue. This is not the data that we're interested in. Otherwise, if we don't continue, we're going to say data.append line. So then we have the raw data and we can define the columns now. First of all, what's the problem here? Oh, we need to remove the if. What's the problem now with dataset txt? I don't see the problem. Oh, of course I see the problem. I need to also open. And then we have starts with. Okay, come on. What kind of code am I writing here? There you go. So that's the data now. And now we can also define the columns. The columns are obviously going to be the attributes. So we have here these attributes. Those are the columns. What we want to do here is we want to get the lines where we have attributes. We want to get the second word here. So we want to split on spaces and we want to get the actual column name. So what we're going to do here again is we're going to say columns equals empty list with open dataset txt in reading mode sf. Actually, we could combine these two statements, but I'm just going to do it like this now. We're going to say if or for line in f read split on line breaks. What we're going to do is we're going to say if the line starts with an at. This time we're not going to continue. We're going to, or actually let's say with an attribute. This time we're not going to continue. We're going to just append this second word in that line. So basically line, split it on white spaces and pick the index 1, which is the second position, and append this to the columns. That's that. Run this. So now we should have a list of the column names, which we do have, and we should have a list of data, which we also have. With all of this here now, we're going to write this into a CSV file so that we can easily read this into a pandas data frame. So we're going to say with open, maybe there's an easier way to do that, but I'm going to do it like this, df.csv in writing mode sf. We're going to say f write. First of all, we want to have the columns. So we're going to join the columns here on a comma, since we have a comma separated file. Join the columns. Then write a new line. And then write another new line, or actually multiple new lines, because we're going to join on the new line character the data. That is that, and this is now a CSV file, and I should be able to load this now here as a CSV file into a pandas data frame. So pd.readcsv df.csv, and that should almost be it. We need to say columns equals columns, and then we have our data set loaded as a pandas data frame. So you can see here, I'm not going to go through all the features, but essentially we have how much time is left officially. So basically the clock. Then we have the score. We have the map that we're on. This might also be important. By the way, you can also use this data set not only to predict the winner, you can also analyze how different maps or how different factors, how different factors are more important on specific maps. This is also something that's quite interesting. You can see if the bomb is planted, you can see the health of the team, you can see the armor. It's always about the full team. It's never about specific players. So you don't know if you have if you have health of 100. You don't know if you have 4 players with 25 HP or if you have 1 player with 100 HP. So yeah, and then in the end, this is the most important one. We have the round winner, CT or T. And each round must have a winner. You can have a match tie, but the round has to have a winner. That is that. What else can we do here? Or not what else can we do here? What can we do here? What do we have to do here? Since we're doing machine learning, since we want to predict something, we have to turn this into something that can be understood by machine learning models. We cannot predict CT or T. We need to have numbers. And because of that, we're going to categorize, or we're going to encode these categories. So we're going to say df, and I want to turn this not only in a categorical feature, I want to turn this into a binary feature, meaning I'm going to say yes or no, did the terrorist side, the T side, win? So I'm going to say T_win. By the way, just for clarification for those of you who don't know what CSGO is, it's a game. So when I'm talking about terrorists, I'm talking about a video game. Don't get any wrong ideas here. Just playing it safe here for YouTube. So the T side win is going to be our feature. It can be yes or no. Did the T side win or not? And this is going to be df.roundWinner, which is the feature, as_type, or no underscore, as type category. We're going to get the category codes. So now we have a new column in the end representing a 1 for a T win and a 0 for a CT win. That is that. What else can we do? We can, first of all, see the correlations of this data frame. So we want to see, okay, of the features that I already have here, of the numeric features, which one of those are correlating very highly with the target variable that I'm interested in. And how can we do that? We can say import matplotlib.pyplot_splt, import seaborn. And I can say here that the correlations are going to be df columns. Now we need to add here also the t-win column, since it's a new column that we just created, like this. And we just calculate the correlation. We can print the correlation as text if we want to, which we can do. Actually, let's do it first. Let's first print the correlations as text so we can see which of the features are actually important. Then we're going to filter out all of those that are not correlating at all or not correlating enough. And then we're only going to visualize those that are actually interesting. So we're going to say here print correlations, but we're going to say we only want to see the correlations for the T-win, and we want to apply the absolute function onto this. Why? Because it doesn't matter if it's correlating highly or not highly, if it's correlating positively or negatively. If I have a correlation of -1, it's a very high correlation. If I have a correlation of 1, it's also a very high correlation. What I don't want to have is something close to 0. So negative or positive, if it's close to 1 or -1, it's a high correlation. So I don't care about negative or positive. I want to know if I have a high correlation in any direction. So I'm applying the absolute function here. I want to sort the values then in a descending order so that I have the highest correlating attributes at the top. Ascending equals false, and then ilog, and I want to have the top 25 features so that I don't see all of them. Let's print this. Let's see if this works. There you go. Now, obviously, T-win correlates with itself, but the highest, the attribute that correlates the most with a T-win, at least in an absolute sense, probably negatively. The higher the CT armor, the more unlikely a T-win. But since this is an absolute value, this is a positive number. It is probably negative 0.33. So that seems to be the most significant one if you just look at the individual features. This one has a correlation of probably negative 0.336. And then you can see all the others. So you can see that the lowest one here has 0.13. So we're going to just limit ourselves to the top 25 most correlating features, because we do have a lot of features. We have 98 columns here, or 97 if we exclude the one that we just created here. So we have 96 features, and this is maybe just too much. So let's focus on the 25 here. Not too much in terms of capability. We can't train them all on those features, but maybe it will add more noise than information. So let's just focus on the top 25 most correlating, highest correlating features. And we're going to do that by selecting columns. We're going to say selected columns, or actually, are we going to take the top 25, or are we going to, let's look for values that have a threshold, a correlation over 0.15. So basically also remove those. Let's say selected columns is going to be equal to an empty list. We're going to say for column in columns plus T-win, since it's also now part of the columns. we're going to try if the absolute value of the correlations of that particular column with t-win, if that correlation, the absolute value is above 0.15, then we want to append this column to the selected columns. Otherwise, not. Otherwise, we're going to not do anything, but in case something goes wrong, if we have a key error or something, I don't know actually why I have this in my prepared code. I think this was because I had some issues when I was running this. Let's just keep it like this. Doesn't hurt. But maybe you can try to do it without a try statement. I'm going to try it without a try statement. Let's see what the problem is here. Or if this is just something that I forgot to remove. And then we're going to say df selected equals df selected columns. Like this. Okay, we do get, no, we don't get a key. Oh, we do get a key error. So let's, I think this is because, yeah, of course, the problem was, I remember now, we have some features that don't have correlations because they're not numerical. So map is not a numerical feature, therefore it doesn't have a correlation. We cannot calculate a correlation here, so it's not going to be included. So we're just going to say here, again, try except key error pass. What's the problem now? I thought I was handling this. Oh, we need to do the try up here. That's the problem. There you go. And now we have a data frame with only a couple of features, 21 columns here. You can see those are the most important features, as it seems. And you can also see that, for example, looking at this list here, how many flashbangs the T side has is correlating higher with whether the T side wins or not than how many AWPs they have. Now, I don't know if that interpretation is entirely correct, but at least when you look at the raw numbers, this seems to be the case. So let's just keep it like that. Let's just say that this is the selected data frame that we have. And now let's visualize this correlation heat map. How do we do that? We just say plt figure to define the size. The figure size, so that we see something here, is going to be 1812. And then I'm going to say SNS heat map. So this is Seaborn with an alias. Heat map, df selected correlation. We're going to sort the values here by the t-win column. We're going to show the annotation so that we see the actual correlation value, and the color map is going to be my favorite one, yellow, green, blue, like this. What's the problem here? Didn't I import Seaborn? I did, but I didn't give it the alias SNS. So let's run this again here. And now we see the correlation heat map. That's it. You can see here the rightmost column is the t-win. And here you can see that it has a high correlation positive with the helmets, the amount of helmets. Now, this here, by the way, is probably a little bit biased, because that does not necessarily mean, for those of you who know something about CSGO, that does not necessarily mean that a helmet is so important. It basically means that when you don't have a helmet, you're ecoing probably, you don't have enough money. So it's not just about the helmet, it's maybe about the fact that you already got some headshots. Maybe you're on an eco round, something like that. So it doesn't necessarily mean that the helmet is basically saving you the round. And then you can also see here CT armor, CT helmets being negatively correlated. So this is just the correlations now. We want to build a machine learning model. So let's see if the features are distributed in a way that will not bias our machine learning models. Let's say df selected. We want to plot a histogram of the numerical features. The figure size is going to be 1812 again. And what we see here is that we have some features that are kind of skewed, like the health, the armor, stuff like that, players alive. Maybe we need to do some transformations here. But before we do that, let's check if we have all the data, if we don't have any missing values. And we don't have missing values. Okay, so that's fine. With the info function, you can see if you have any null value. So if you see everywhere this number, but then you see one feature where this is not the case, maybe you have some missing values, so you might have to impute them. In this case, we don't have to do that. So actually, I'm not gonna scale anything here manually. I'm not gonna lock transform any features. I'm going to just use a scalar, so the standard scalar, and we're going to see what the results are with this. So we're going to just build, first of all, a simple k-neighbors classifier, a very, very simple classification model. We're going to then move on with the random forest classifier, and we're going to also look at a neural network later on, at a deep neural network. Maybe not so deep, maybe just a couple of layers. But we're going to start here with a simple train test split. So we want to have training data that we can train the model on and testing data that we can evaluate the model on. So we're going to say from sklearn dot model selection, we want to import the train test split. And we're going to say here that, not scalar, we're not going to scale yet. Or are we going to scale? Maybe we should, no, let's split first and then scale. So, because we also don't want to, we need to split first because we don't want to scale the output. We don't want to scale the final results necessarily, even though I think it wouldn't make too much of a difference here. But nevertheless, we're going to start by saying x and y is going to be equal to the selected data frame dropping the twin column, because the x value should be everything except for what we're trying to predict. So we're going to say here, oh, I have caps lock enabled. We're going to say here, drop the twin on axis 1. So drop the column twin for the x values. And for the y values, we want to have only that one column twin, like this here. And then we want to say x train, x test, y train, y test is going to be a train test split on x and y with a test size of 0.2, 20%. That is a simple train test split. We can see now the length of x train is 97,000 entries and of x test is 24,000 entries. So we have quite a lot of data here. So let's go ahead and say now from sklearn, which is scikit-learn, import preprocessing, or from sklearn.preprocessing, import first of all the standard scalar, and then from sklearn dot neighbors, we're going to import the simple k-neighbors classifier. We're going to say now that the scalar is going to be a simple standard scalar. We're going to say xtrain scaled is going to be scalar.fit transform xtrain. And we're going to say xtest scaled is going to be scalar.transform. We're not going to fit again because we already fit the transform. We're going to just transform on xtest. We're going to transform xtest into xtest scaled. And then we're going to train a simple k-nearest neighbors classifier, the k-neighbors classifier here. We're going to fit it on xtrain scaled with a target of ytrain. And it's already trained. Now, training a k-neighbors classifier basically means doing nothing because the actual work is being done when you add a new instance that you want to classify, because the k-neighbors classifier works with a distance measure. So actually, you don't need to train anything. When you add the data itself is the training. And when you want to classify something, you need to calculate the distances. So what we're going to do now is we're going to say knn.score, and we're going to score our test set. So xtest scaled, ytest, and hopefully this doesn't take too long. There you go. We already have a 76.42% accuracy. This basically means, in clear words, that this model, when you give it information about the armor of the different teams, the helmets, whether the bomb is planted or not, the money, the different weapons, all these features that we have above here, whether they have diffuse kits and stuff like that. If you give it all this information at a random point in time, or at least in the 20-second intervals, this means that this model will have a 76% accuracy when telling you that the T side or the CT side wins. And this is just with a simple k-neighbors classifier without hyperparameter tuning or anything like that. So speaking of hyperparameter tuning, let's go ahead and try it. Let's go and use a grid search to find some more optimal parameters for this k-neighbors classifier. Let's say we have from sklearn dot model selection, we want to import a simple grid search, CV, cross-validation, and we want to use the following parameter grid. We want to have n neighbors set to different values. So we want to have a list. Actually, not a list. Let's actually use a random search, randomized search CV, because maybe this will take too long otherwise. So neighbors, list, range, and then go from 5 to 17 with a step size of 2. And then go with 2 different kinds of weights. We have the uniform distance, or actually the uniform way of evaluating the neighbors, and the distance. So in terms of when you have weights distance, instances that are closer to you will have more influence on you, on your classification. So we have this parameter grid. We're going to create a new k-neighbors classifier. Here we're going to say n jobs is going to be, this is the number of cores that we're going to use. I'm going to use 4 cores. If you provide -1, it's going to use the max number, but since I'm recording, I'm just going to provide 4 here. And I'm going to say that the classifier, the final classifier, is going to be randomized search CV, KNN. So this is basically the randomized search classifier. And then from that, we're going to get the best estimator. So this is not the KNN. We're passing the KNN, we're passing the parameter grid. We pass n jobs being equal to 4 again. We pass n iterations being equal to 3. We can print some more information. So let's print verbose equals 2. And we want to have 3-fold cross-validation. And then we're going to say CLF fit on X train scaled and Y train. So this is now going to just do hyperparameter tuning, trying to find the most optimal parameters here, the best number of neighbors to look at with the better scoring method, with the better weight method here. And once we have the results, we do have the results already. We can get here from this classifier now the best estimator, which is this one here with 7 neighbors and a distance weights measure. And we can take this best estimator, let's save it as KNN. We can take this and score this now on X test scaled and Y test. And let's see, it has an even better performance, 78.22% accuracy, which is better. Now, due to the nature of this problem, looking at different parameters, oftentimes binary or just having some limited categorical choices, you can only have 5 diffuse kits, 0, 1, you can have 0, 1, 2, 3, or 5, 0, 1, 2, 3, 4, and 5 diffuse kits. You cannot have 6, or you cannot have -1, so you have a very limited choice, which means that decision trees might be a good model here. Sorry. So basically looking at the different factors, saying yes, no, or less than or greater than, and then deciding on which team wins. This is a very natural way to think about this data set, about this problem. So maybe decision trees can be quite powerful. Maybe random forest classifiers can be quite powerful because they combine multiple decision trees. Let's see if that's the case. Let's go ahead and say from sklearn.preprocessing import actually I did import the standard scaler already. I also have this scaled data, so I'm not going to scale it again, but we're going to say from sklearn.ensemble, we're going to import random forest classifier. And we're going to say that the forest is equal to the random forest classifier n jobs, and underscore jobs is going to be 4. And then I'm going to say forests.fit X train scaled, Y train. And let's see, there you go. We have a random forest classifier, and now we can just go ahead and say forest.score X test scaled, Y test. and we get an accuracy of 82.91%, basically meaning that if you ask this random forest classifier with the information that we have, who's going to win 82.9% of the time, this is going to be correct. This is quite impressive because I don't think that I could do the same thing. Now, maybe I'm overlooking something in terms of, sometimes it may be quite obvious because most of the time it's towards the end of the round or something. But I don't think that if you ask me looking at this game at different rounds, whether the C team or T team will win, that I will give you a almost 83% accurate answer. I think I'll be wrong quite often. So this is quite impressive. Now, finally, let's build a neural network. Let's do it with a neural network from TensorFlow, and let's see if we get even better results, which I don't think, because as I said, the nature of the problem is very similar to how decision trees work. So I think that decision trees will probably, or random forests with a lot of decision trees, are going to be more powerful for this particular data set. But let's see what happens when I say from TensorFlow import keras, and here we're going to define a simple structure. We're going to have a simple feed-forward neural network with 3 dense layers with 200, 100, 100 neurons, and then an output neuron saying yes or no, essentially. So being a binary neuron, this is going to be not as so often the softmax function. It's going to be a sigmoid activation function, so it's going to be how likely a win is for the team, essentially. Or not how likely it is, it's going to go towards the 1 or towards the 0, essentially. So we're going to say here that the model is going to be a keras.models.sequential model. We're going to then say that the model has to have a new layer, keras.layers input layer, first of all. The shape is going to be, how many features do we now have? Let's just see. X-train scaled, maybe not scaled, so that we can actually see the data frame. Come on. 20 columns. Okay, so the shape of the input is going to be 20, but it's going to be a tuple, so 20 comma. And we need to close the brackets. Then model at keras layers dense. And it's going to have 200 units with a simple activation function called ReLU, rectified linear unit. We're going to copy that. We're going to change this here to 100, 100, and then we're going to have one final output layer, which is also going to be a dense layer connected to all the other neurons with the sigmoid activation function. So we have that. We're going to compile the model now. Model.compile. Loss function is going to be a binary cross entropy, since this is a binary classification. The optimizer is going to be atom, and the metrics that we're interested in are going to be only the accuracy. That's that. The model is compiled, and now let's go ahead and implement early stopping, basically meaning that if we have a certain number of iterations without any progress, we're going to stop early. So we're going to say early stopping callback. We're going to say that this is a keras callback early stopping with a patience of 5 iterations, I think, or 5 epochs. Is it epochs? Yeah, 5 epochs without improvement. And then we're going to say X-train scaled train. So we need to have a validation set. So X-train scaled train. Maybe you can come up with a better name. X validation, Y train, train, and Y validation is going to be a train test split again. So we need to have a validation set for the callback for the early stopping. We're going to provide here X train scaled and Y train as an input with a test size of this time 0.15, 15%. And then we're going to say model fit. We want to fit the model on X train scaled train, Y train train. We want to have 30 epochs unless we have to do early stopping. And the callbacks that we're passing here are going to be just early stopping. And the validation data that we want to use for this is we want to use the X valid and the Y valid. That is that. Let's fit the model. It's going to fit it. And if it doesn't have enough progress for 5 epochs, it's going to basically stop and give us what it has. And with that, we can also see the accuracy here already on the validation set. It's not as good as the random forest. It's also not as good as the KNN. Now, one thing about the random forest, by the way, we didn't do any hyperparameter tuning here. We didn't do a grid search. We didn't do a randomized search. If you optimize it, you will probably get an even better result. And if you change some stuff about the features, maybe you include some other features, you remove some features, you make it better and better, you will probably end up with a accuracy around 85, I guess. So here we got early stopping, epoch 15. Now let's go ahead and say model evaluate. We want to evaluate the model on X test scaled and on Y test. There you go, we get 75%. This is the worst model. Now, to be fair, I just picked any structure. Maybe you can make a better structure. Maybe you can use less neurons, more neurons, less layers, more layers, different activation functions, different types of layers, and you can get better results. But with this simple structure here, we get only 75% accuracy. So the winner in this particular tutorial here is definitely the random forest classifier with an accuracy of almost 83%. So that's it for today's video. I hope you enjoyed it and I hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video and bye.